Okay, our next speaker is Yixuan Li from the University of Padua. We'll speak about the statistics of BPS chaos.
Well, thank you, Henning. So before I begin, let me thank the organizers for organizing this wonderful conference and give me the opportunities to present my work. So today I'm going to talk about the statistics of BPS chaos, and this is work in progress with Nate Cheplak, Stefano Masai, and Masaki Shigemori. This talk is about supersymmetric black hole microstates. And as we have learned from this morning, we know how to count them, and we also know how to describe them from the physics of intersecting branes. But today, we are also interested into the collective properties of those microstates, in particular, the late-time quantum chaos properties. We will start with a question: how does quantum chaos emerge out of supersymmetric black hole microstates? So what is late-time chaos, by the way? Well, late-time chaos is a set of properties of quantum states taken collectively. A prime example of such properties is eigenvalue repulsion. So consider a system, whether it is integral or chaotic. You list all of the energy levels of that system and consider the adjacent levels. So En plus 1 minus En, and you look at the statistics of this. What you will find is a different behavior, but depending on whether your system is integrable or chaotic. For chaotic systems, you will have zero probability for degenerate levels, and you will find a maximum for your function, the red curve, which means that there exists a strong correlation between neighboring energy levels. So they will have some kind of energy eigenvalue repulsion at this scale delta. Another piece of data of late-time chaos is the Thouless time. So 1 over Thouless time is the Thouless energy. This is an energy scale at which all of the energies inside this energy scale have some correlation. Therefore, the Thouless time characterizes how strongly chaotic a quantum system is. If I decide to rescale my microcanonical window to be of order 1 in energy scale, if the Thouless time is order 1, it means that there exists some correlation between all of the energy levels in the whole microcanonical window. On the contrary, if the Thouless time is of order n to the power alpha, it means that the correlation is only between some smaller groups. And so, therefore, I would have weak chaos. In practice, in order to determine the Thouless time, what one does is to draw the spectral form factor, and the Thouless time corresponds to the start of the ramp in the spectral form factor. Now, supersymmetric black holes are also expected to have properties of chaos. And it is possible to define chaos for BPS systems. Well, how do we do this? Well, we can replace the Hamiltonian by the BPS projection of any simple operator. So if O is a simple operator, whatever it means, then O hat is the BPS projection, the projection onto the BPS space of O. And one can evolve this, time evolve this with O hat instead of the Hamiltonian, and compute the Thouless time out of the spectrum form factor. Suppose now that in the basis of microstates, this O hat here is written in that form, such that there are zeros in the off-diagonal parts, and the non-zero parts lie only in a band next to the diagonal. What it means is that, suppose that you are one of the microstates here, it means that you can only interact with your nearest neighbors through this O hat. In that situation, the Thouless time is of order of the diffusion time of that problem, which is the size of the matrix divided by the size of the band squared. Now we are at the Eurostring conference, and we kind of know string theory, and we definitely all love string theory. And the question is, can one estimate the Thouless time for the Schrödinger-Vafa-like black holes for the black hole microstates? For example, the D1-D5P system. Well, what is the D1-D5P system? Consider a space-time of geometry of topology time R4, S1, and T4. Consider some D1 branes that are extended along time, the S1, some D5 branes along time, S1 and T4, and the momentum wave in one of the NOR-like directions of the S1, such that you have a supersymmetric system. At strong Toved coupling, the brane system backreacts into a black hole solution. Whereas for weak Toved coupling, the open strings on the branes describe a super Yang-Milch gauge theory. The low energy limit of that gauge theory at finite GS is a two-dimensional CFT that is complicated to describe, but one can understand it as a deformation of the D1-D5 CFT at the free orbifold point. What is this D1-D5 CFT of the free orbifold point? Well, this is a two-dimensional sigma model on T4 power n modded out by Sn, where n is n1 and 5 is the number of copies of fields on S1. So if x1, x2, xn are the fields on the S1, then the action of Sn, the symmetric group, is to specify the boundary conditions to how to glue the copies together as one goes around the circle. So consider an element G of the symmetric group Sn. Then what the boundary condition tells you is that whenever you go from a copy to another one, when you go around the circle, then you are going to another copy. So you go from a copy to another copy to another copy, and at some point you come back to the copy, your initial copy. This defines you a strand. Therefore, you can have strands of length 1, length 2, and length 3, and etc., etc. So I can call mu, let's say mu I, to be the number of microstates in the number of strands of length 1. I think here they're supposed to have like 3 dots, and 3 dots here, and I think that it disappeared from the PDF. So in the BPS sector has 2 charge and 3 charge states. The 2 charge states are quarter BPS with respect to the 32 supercharges of type 2b string theory, the type 2b vacuum. So it has 8 supersymmetries, and the 3 charge states have 4 supersymmetries, and they correspond to the D1, D5P states. So if I think about 2 charge states, then essentially I have two steps to do. The first step is to specify how the n copies combine into strands. I have to distribute the winding number n into strands of different lengths. And as a second step, I have to choose a polarization on each of the strands. And I have 16 choices on each of the strands. Now I can organize the microstates. I can fix n, and I can regroup the microstates according to the number of strands. So on the left, I put all of the longest strands, so a single strand of length n, and on the right, I put the microstates that are composed of smaller strands, so n strands of length 1. So what Shen, Lin, and Schenker have shown is that there exists a simple operator, which is the twist operator, that acts on the 2 charge states in the following fashion. This means that each group only interacts with its nearest neighbor, which means that we have a banded matrix, and the relative size of the band is equal to the size of the biggest group divided by the total number of microstates, and scales like 1 over square root of n. As n goes to infinity, the band becomes smaller and smaller and smaller. So it means that microstates have lesser and lesser pairs to interact with. And so the Thalers time is going to become bigger and bigger. And therefore, they show that this should correspond to a weak chaos system. This is also in line with the fact that the mean value of the strands is proportional to square root of n log n, which means that the most typical microstate sits somewhere in between, between 1 and n. So it has this amount of length of, well, it's somewhere in the middle of 1 and n. But what about 3 charge states? Can you get strong chaos out of them? So for the 2 charge states, the longest string sector contains only 16 states. That's not much. But the idea is that now if you consider 3 charge states, then you have to consider the momentum in addition to this, right? And we know that adding the momentum should favor long string states. And perhaps that now, thanks to the addition of momentum, then the shape of this sigma 2 hat is going to be distorted in the 3 charge case. And what we like to have actually, is that this longest string sector for 3 charge, perhaps it's going to account for order 1 of the total matrix instead of something that scales like 1 over square root of n. So is that possible? Well, if you think about it, we know that on the longest string, there is the effect of momentum fractionation. So all of the momenta on the longest string have units of 1 over n1 and 5. So it means that you have a lot of choice to put on the longest string. And the longest string carries a huge entropy, and the entropy is actually 2 pi square root of n1 and 5 np. This is the same as the leading order of the black hole. And for simplicity, let me just call n1 and 5 as n and np as p. Okay, so we have a huge entropy, but is that enough for strong chaos? The answer is no, because in principle, you could have that for all of the strands. So the degeneracy for k strands could be exactly equal to, let's say, exponential of 2 pi square root of np for all k, in which case the total degeneracy of the system would be n times this number. In that situation, one would have still the banded matrix, and we will still find that the Thalers time is bigger than something of order n squared. So what we need to do is actually to compute the logarithmic corrections to the entropy as well. And then we can maybe conclude. And in particular, remember that for the 2 charge, the 2 charge states, the mean value of the strands was somewhere in the middle, around square root of n. So now if we want to have something that looks like this, is it possible to show that the mean value of strands is closer to 1 or log of n or something like this, right? So what are the 3 charge microstates? Well, this time we have to distribute among the strands not only the winding number n, but also the momentum number p and angular momentum j. So on the strands we have, okay, this winding number, this momentum number p, and angular momentum j, which means that on the strands we will have also the winding number n, momentum number m, and angular momentum l. And let me call mu the number of such strands. So the number of strands of such strands. And this time the microstates, it consists of decomposing n, p, and j into these factors that depend on mu. How many microstates do I have? Well, this is a counting problem in the microcanonical ensemble. A single strand will carry a degeneracy of, let's say, c. Then mu, so if this is my strand, right, it carries a degeneracy of c. But mu of them is going to carry a binomial factor that depends, well, whose exact expression depends on whether this strand behaves as a boson or as a fermion. And I can repackage all of this into a partition function. So this is what happens for bosons, but I could write the same for fermions. And the idea is to compare the partition function with its developed form. What I can do is that I can look at, for example, the powers. The powers, comparing the powers below and up, will give me the constraints that I talked to you about before. And if I compare the coefficients, then this would tell me that the black hole degeneracy is the number of ways to distribute the charges while accounting for the symmetrization, like the bosonic or fermionic symmetrization. But what we're interested here is not only this degeneracy, but also to track down the number of strands within the degeneracy. So we have another constraint on the number of strands S. So that's one approach. And the second approach is to go to the grand canonical ensemble. So we can write P, Q, and Y as the fugacities and introduce inverse temperatures. The system thermalizes, and the mean values of mu's is going to depend on the occupation factor and the density of states. The unknowns in this problem are the inverse temperatures, but what we know are actually the black hole charges that we can measure, let's say in supergravity. So N, P, and J, they are known. We can invert these equations and write beta N, beta J, and beta P in terms of N, P, and J. And then the mean value of strands will be given by this expression. And we can deduce also the higher moments as well, and such that the end result will tell us whether we are into a situation that looks more like a weak chaos situation or a strong chaos situation. I could also play the same game, but with the index as the partition function. And if I do that, things get simpler, and they get in a more compact form, such that I can use the modular properties for the automorphic forms and solve for beta n, beta j, and beta p, with the index replacing the degeneracy. So writing some fields in terms of N, P, and J, might be familiar to you. This is actually the attractor equations for the axial dilaton. So somehow, to say that the thermalization of the microstates in the ground canonical ensemble with the index as the partition function, this leads to the attractor equations. But what we are interested in is the thermalization with the degeneracy as the partition function. And this will tell us about the statistics of microstates into groups of how they organize themselves according to groups of different strand lengths. And this, in turn, will tell us about the potential of black hole microstates to exhibit strong chaos or not. So all of this is still work in progress, but I can already tell you that there is a caveat. This analysis is at the free orbital point. And of course, the strength of chaos can differ whenever I go to higher values of GS. However, we do believe that the analysis is still important, because I started with this question: how does quantum chaos emerge out of supersymmetric black hole microstates? And imagine that we find that, I don't know, like there is already strong chaos at free orbital point, or on the contrary, that we find that there is not strong chaos at free orbital point. Then this will tell us something, right? It can tell us about whether strong chaos can only emerge as a gravitational effect or not. And by the way, if the answer to this question is yes, then another question that is still very relevant is how far away from strong chaos is the free orbital point? So I think I can conclude. So we have looked at the possibility of strong or weak chaos for D1, D5P systems. We have shown that this is related to how the microstates organize themselves into groups. And this is related to the logarithmic corrections of groups of different strands. All of this is related to, gives us a statistical physics problem encoded in the density of states at the free orbital point. And it has two aspects. The first as a counting problem in the microcanonical ensemble, and the second as a thermalization problem in the grand canonical ensemble. And as an outlook, the statistics of BPS chaos can teach us several things. First, it can teach us about the lifting problem, about the statistics of the states that become non-BPS when one tunes GS to be non-zero values, depending, let's say, on the value, on the number of strands that decompose the macrostates. Secondly, it would be interesting to go and talk to the fortuity community. So if you think about fortuity, usually it's something that depends on only n, whereas here this analysis of chaos seems to depend on n and p, and above all the formulas are actually almost symmetric between n and p. So is it possible to define a notion of fortuity that depends on n and p and see that there is a symmetry between n and p? And to end this talk, I'll go a little bit speculative. Perhaps you could tell us about the swampland. So we don't know what is the origin of the distance conjecture, well, what if the principle behind the distance conjecture was that the minimal black hole in an EFT should have strong chaos? Thank you very much.
Thank you. Questions?
Thanks for the nice talk. So in this index example that you mentioned,
yeah,
one might expect that there is no strong chaos. Does that bear out?
So we are still doing the...
Because that should be easier to do than what you eventually want to do, right?
We are still doing the computation.
Even for the index? I see.
Yeah. There's something that I would like to talk to you. It's about the lifting problem. So we are finding that there is a number of states. So in the degeneracy of the longest strands, we find that there is more states in the longest strand sector at the free orbital point than the black hole at like the black hole solution at non-zero. So I wanted to have a chat with you on, because that would mean, if we are not mistaken, that even on the longest strand, most of the states are going to become to lift, and well, this is a surprise for me. So yeah.
Another question. So one thing you said was very interesting, that if this chaos doesn't arise at the free point, we expect it at the gravitational point,
Right.
then you can try to estimate where it comes. So you said at what distance will it appear?
Uh-huh.
How are you thinking of calculating that?
Well, so okay, maybe this is like related to my PhD, where I did my PhD. But usually we think of those kind of black hole microstates as some kind of fuzzball solution, so with a very deep throat and with a smooth cap. I mean, even if it's not, well, the idea is that between the asymptotics and the smooth cap, there is a huge blue shift, right? So if you think about this sigma 2 operator in the gravity sense, then the equivalent would be that, okay, so suppose that you start with some Lewin-Method geometry, and you Fourier decompose its shape. And so the idea of the sigma 2 is that you would change one of the coefficients of this of this shape. Now, if that's your operator from your very far away from infinity, then there is a chance that whenever this action goes to the deep into the throat, then actually it talks to all of the different modes. So this could be one of the possibilities. Yeah.
Okay, there's no further question. Let's thank you, Yixuan, again.